Hi, my name's Dana Humphrey. I'm Dean of the University of Maine College of Engineering. It's my pleasure to welcome you on this tour. Oh, and by the way, everybody just calls me Dana. What we're going to be doing today, we're going to be going on a tour through some of our labs, and I'm also going to tell you a little bit about the College of Engineering. At the UMaine College of Engineering, we have 11 different engineering and engineering technology majors. We're a full-service College of Engineering, and I want to say a word or two about the difference between what does it mean to major in engineering versus what does it mean to major in engineering technology. Engineers tend to be more focused on the design side of things. Engineering technology graduates tend to be more focused on the production side. A really simple example, a civil engineer would design a bridge. A construction engineering technology graduate would be in charge of building the bridge. It's not a matter of one's more prestigious of another, one gets paid more. It's just, do you want to be more focused on the design side or production side? Another example, a lot of our graduates go to work for Pratt & Whitney. They hire mechanical engineers to design the next generation of jet engines, mechanical engineering technology graduates to take and actually produce those components. High demand, high pay, but I just want to kind of set the stage, especially for those of you who are trying to pick between an engineering or an engineering technology major. One of the things that's most important for you to know when you come here as a UMaine engineering student, we are a very hands-on program. You're going to be taking engineering courses from your very first semester until the day you graduate. I'll give a couple examples. Civil engineers in their first semester are taking a course called Materials, where you learn about concrete, steel, wood, plastics, the things that civil engineers build with. The course is taught by Eric Landis. He's a distinguished Maine professor. That's the highest award that a faculty member on this campus can get. The students rate the faculty on a scale of 1 being perfect and 5 being not breathing. Eric's rating is usually about 1.1. He's as close to perfect as you can get. It's got a lab that goes along with it, and a critical thing for civil engineers to know is how strong is something? Well, how do you find that out? You actually take things and load it to failure. You break it. So what you do is you get college credit for breaking things. What could be more fun in your first semester than that? Other majors, for example, electrical engineers, they're making payloads for scientific ballooning projects in their very first semester, because we want you to experience the fun of being an engineer right from the start. Certainly, as you take and work your way up through your semesters, you'll be taking more and more engineering courses, and certainly some science and math courses to build up the foundation that you need to be an effective engineer. And by the time you're a senior, you're taking almost all engineering courses. All of our students in their senior year do a senior capstone project. We do this as a group because engineering is a group sport. It's not an individual sport. So you want to simulate that here. And these are real projects. Some example projects, civil engineers designed a retreat for wounded veterans in central Maine. Mechanical engineers, they converted a snowmobile that run on gasoline to take and change it to running on compressed natural gas. Great engineering challenges, and we want you to really have that be your culminating experience. Now, when you graduate, the demand for our graduates is very high. We have an engineering job fair every October. This past October, we had 170 companies that came here. Literally, they were competing against each other to hire our graduates. That's because they know the quality of a UMaine engineering graduate combined with very high demand for engineers in the workforce. Our placement rate for our last group of graduates was 99.9%, meaning they're either employed full-time or in graduate school full-time. That is as close to perfect as you can get. Before you are at the point where you're taking and getting your full-time job, you also have the opportunity to take and get an internship. 80% of our graduates have at least one significant internship opportunity while they're a student here, and that really takes and sets you up for that full-time job. So what we've done is kind of done an overview of the college. We have great opportunities for students to participate in the honors program, study abroad programs, and now what we're going to do is going to start taking a look at some of our laboratories. So our first stop is the Advanced Manufacturing Center. This is a place where we work for companies primarily in Maine to design new products, design new processes, build production facilities. To go in this lab, we need to have our safety glasses. Let's put on our safety glasses and let's follow me into the lab. Follow me. So here we are in the Advanced Manufacturing Center. It is a very large facility. We have about 15 students who work here and about 3 staff members. This is a place where students get real hands-on experience. Let's look at some of the cool toys we have here. Follow me. This device here is a 3D printer. I bet most of you have used 3D printers to print in plastic. This one actually prints in metal. Primarily, we're printing in stainless steel. The feedstock for this comes in these little tubes like this here. This is a mixture of finely ground particles of metal combined with wax. It extrudes the material just like you would for a machine that prints in steel, or prints in plastic rather, and it prints objects that look like this. So this is an example of an object where this is just kind of some funny shapes to show the capabilities. This is now a mixture of steel and wax. How strong is wax? Not very. So we take this and put it in a second machine that takes and dissolves out most of the wax, and then we take and put it in a furnace that heats it up and fuses the particles together. This is a part that's in stainless steel, and let's take a look at it, what it looks like once it's gone through the unit. So now we've taken, so here's the original part, here's the part at the end of the process. You should notice it's shrunk a lot because you've removed all the wax, but it shrinks in a very, very precise manner. This process where we're taking and using this to take and make these parts is called an additive process, where we take and add material until we get the part that we need. And the contrast for that is the old way of making parts out of metal. You just start with a chunk of the metal and you start cutting away material until you're left with the part. Now we can do the reverse. We're just adding material until we get the part. We have a lot of different things that we make. This is just a little fun part that we did. There's the finished part. This is actually a knob off of an antique car. We needed to take and do a replacement because you couldn't go down to the auto parts store and buy one of these. So someone brought in the broken part. We used another one of our cool machines, which is over here. It's this device right here. This is a 3D scanner. So you can take the actual physical part, do a 3D scan of the part, and now you've got a 3D computer model of the part. We then took that computer file, put that into the machine that prints to print the part. This is how the part looked like as it was printed. It had support material, which is this part down here. Then we're able to take and separate out the actual part. You notice that the end of this is threaded. This machine is not precise enough to be able to actually print threads, so we made that with a conventional technique with something called a die, where we took and made that part. So this is the place where you can get access to cutting-edge technologies. So now let's take and go out into the larger part of the lab and look at some of the cool things that are happening out there. So everybody follow me. So now we're back out in the big part of the lab. Okay, to open here? Okay. So we just looked at a system that was an additive system. This is a computer and numerical controlled milling machine. What we do is we start with a chunk of the base material, metal, plastic, whatever, and then we take and cut away the material we don't want. Inside it has a cutting head that takes and rotates to cut away the material, and the bed moves Side to side, this direction, side to side in that axis, so that's 2. Up and down is 3. And it can also rotate the part, so it's 4. So this is a 4-axis milling machine. This machine is smart enough, if we take a look, let me close it back up, and we take and look out on the end here. If we look up here, you've got a numbered drum up there on the end that actually holds the cutting tools. This machine is smart enough that when it gets done with a particular cutting operation, it stops, put the tool that it's using back in the holder, and then takes the next tool and then does the cutting operation with this. So again, this is a CNC milling machine. This is a 4-axis machine. We actually have a 5-axis machine that we're getting ready to order. So it can, in addition to rotating the part, it can also tilt the part, and then it has the ability to do laser deposition of metal on the surface of the parts. So this is very, very cutting edge technology that we have here. So let's take a look at some of the other things that are happening in the lab. So we have behind me here, this is a set of collapsible bleachers. This is like what you'd sit on at a high school sporting event. So you've got the sporting event, they take and roll the bleachers out, everyone sits there, and then the event is over, they roll them back so you can have more gym floor space. It's almost certain that no matter where you live, that these were made by a company called Hussey Seating that's located in North Berwick, Maine. They make these in Maine and install them all over the world. Now, the critical thing for these stands is when they're full of people, it's the game for the state championship. The home team scores the point that allows them to win the game. And what does everybody do at the same time? They stand up and they start jumping up and down. Now, what an engineer says, that puts loading on the stands. So, and as an engineer, especially if you're the right kind of engineer, you have the ability to estimate how much load that's putting on the stands. But you still need to be able to have the ability from time to time to check to make sure your calculations are right. And that's why Hussey Seating used this lab. What they did is they built one of their conventional stands here, so nothing special about those. Then we instrumented it to measure how much force there was in some of the critical components. We recruited a bunch of college students that jumped up and down on command while we took measurements. So this theme of engineers being able to take and estimate how things will behave, but still needing to measure how they behave is absolutely critical. One of the students who worked on this project, he goes by PJ for his first name, and he worked on this project here in the lab. I happened to be at Hussey Seating to meet with their president, Gary Merrill, and there was PJ there. He was dressed up like I am today. He had his sports jacket on and his tie. His hair was neatly combed. I go, PJ, what are you doing here? Well, I'm interviewing for a job. Well, who do you think hired him? Hussey Seating, because PJ already worked for them here in the lab. I see their president quite frequently, and I ask him, well, how's PJ doing? He's doing great. He says, we need more just like him. That's the kind of opportunities you can get by working in a lab like this. So let's look at some of our other projects that are very active. So as we take a look right behind me here, that is a robotic arm that we're modifying for a company in Maine, a company that makes ballistic resistant panels. This is our panels used by the U.S. military to provide protection to our forces. What this particular device is going to be modified to do, this is going to be modified to be able to take and pick up the panels, smooth the edges of the panels, drill holes in the panels at the appropriate places. So students who work in this lab get hands-on experience with large robots like this. And the purpose of labs here, again, is to take and allow our students to have these great hands-on experiences. I've got one more thing I want to show you, so let's take a walk up this way. So what we're looking at here, this is an area where we're actually investigating the effect of head trauma. So there's a lot of concern in high school sports, professional sports, college sports with repetitive head trauma. So what we have here is we sawed off some poor fellow's head and mounted it on this frame and we instrumented the head so we can measure how much force is imparted to the head. We put it on this frame here that's off to the side, and what we do is we take and we pick it up and we drop it. We measure how much force is imparted to the head. So we've measured the force, then we take and put on head protection gear. We pick it up, drop it again, measure the force, and the difference is how much force is absorbed by the head protection gear. And of course, the name of the game is to maximize the amount of force that's absorbed by the head protection gear. Now, the way that we take and do that to take and really improve the cushioning is we develop new cushioning here. This is a honeycomb material that takes, and as it gets compressed, actually crushes. And that takes and greatly increases the energy absorption. So let's just pause for a moment and think about this particular problem here. We have this head that we're picking up and dropping it. What engineering major would be best suited to study this type of problem? So any of you who are thinking biomedical engineering, I'd say that's second best. There's actually one more that's even better to study this problem, and that's mechanical engineering. But you might be thinking, but Dana, isn't that really to take and study things like cars? And of course the answer is yes. And if the problem was cars driving into a bridge abutment, I'm sure mechanical engineering would have come immediately to mind. But mechanical engineers are really good with things that are moving that come to a sudden stop. It could be a head hitting the floor, it could be a car driving to a bridge abutment. It's exactly the same problem. So mechanical engineers are actually ideally suited to studying things that are moving objects. Now myself, I'm actually a civil engineer by training. I'm not very good with things that move. And in fact, if you're out with me visiting one of my civil engineering projects and it starts to move, I'm going to shout run, because that means it's failing and we're getting out of there. So the point of this lab here, it's a place where we work for real companies on real projects where students get real experience. And this is one of the great labs we have at the University of Maine. Now we're going to transition to our next lab. So now we're at the Advanced Structures and Composites Center. To go in this lab, we need to have both hard hat and safety glasses. So let me put on my hard hat and safety glasses. Blue hard hat means you've got safety training. You're going to take and put on one of the white hard hats and safety glasses. You're going to follow me into the lab. So let's take and swipe into the lab. Come on in. So what we do in this lab is we conceive of, design, fabricate, and test the next generation of building materials. This takes a lot of different forms. So if we take a look at what's behind me right here, this is a system to decelerate manned spacecraft as it goes into the Martian atmosphere. So here's the engineering problem. The spacecraft is going through the vacuum of space at something in excess of 10,000 miles an hour. By the time it contacts the surface of Mars, it has to be going very close to 0 miles an hour. If it's not, you have what an engineer would call a crash. So what we have is a system here. These are a series of inflated rings, kind of like donuts. The official name would be a toroid, and we stack these up into a big inverted pyramid. And what this does is it creates a lot of cross-sectional area. Think about this as an upside-down umbrella, okay? Creating a lot of cross-sectional area, and that creates drag. So the engineering solution to this problem, and again, engineers solve problems for a living, is to take and have something that's going to create a lot of drag as it goes into the Martian atmosphere to take and slow it down. Our specific role in this is we have underneath this, we have a series of pistons and cables that take and connect to the donut. We can take and pull on them and measure how this behaves. Now, is it okay for an engineer to think, okay, we've got a good idea, we put some astronauts in a capsule, send them off to Mars, and just see if it works? And it's like, oh no, they crashed into Mars, we'll just try it again. You've got to do a lot of testing on Earth to make sure we've got it right. So what we do is we take and study the structural integrity, we take and pull on it, If we look way overhead, we have a series of cameras that look down on this, and without touching it, we monitor how it behaves. We monitor how it performs. One of our faculty members, Bill Davids, he is an expert in inflated structures. NASA actually came to Bill and asked him to do this work. Now, Bill's a civil engineer. You might be thinking, isn't this more kind of like a mechanical problem or something like that? Well, maybe, but one of the things to be thinking about, no matter what you major in engineering, is that any individual field is very broad. What you can do with that is a broad swath of things. It's not one little narrow defined thing. So with Bill's expertise and his expertise in inflated structures, yes, it can be applied to temporary buildings and things, but it's equally applicable to NASA. So that's what we're taking and working on with this particular project here. This project had 6 undergraduate students working on it and 2 graduate students. Now we're getting ready to take and switch to the next phase. Right now we have one of our seniors in civil engineering. She's the lead on this particular project. This lab as a whole has over 100 undergraduates who work in this lab. So let's go take a look and see what's else is going on in this lab. And by the way, we're in the small part of the lab. Next, we're going to go into the big part of the lab. So follow me. Just a quick stop along the way. This is our Bridge in a Backpack, which is a technology that we developed here at the University of Maine. Undergraduate students were integral to solving this problem. Now, when engineers solve problems, they're very, very complicated. And one thing that you're going to learn is you're going to learn how to take big, complicated problems and break them up into smaller problems. 2 of the early small problems that we had to develop, we wanted to have these tubes here. These are some examples of tubes. Where we've got these tubes here, where we've got a liner inside, they've got fabric, and what they start as is they start out as just cloth with a bag on the inside and a bag on the outside. You take and use a vacuum to draw in the resin. One of the early problems we had is these are going to be in the shape of an arch, but it caused wrinkles on the bottom of the fabric. What we had is a group of 3 undergraduate students. These were civil engineering students between their first semester and second semester. Their summer job was to take and determine what weave of fabric was going to be the best to take and get something curved into the shape of an arch with no wrinkles. Another problem that we had is these are ultimately going to be taken and filled with concrete. And concrete, when it cures, naturally shrinks a little bit. It was actually shrinking away from the wall of the container. So another group of civil engineering students investigated different type of chemicals they could add to the concrete when it's being mixed to cause it to take and expand a little bit. So you got firm contact between the concrete and the walls of the container. Those students did a great job. They figured out what the admixture should be or the chemicals should be. The only downside was they did a very poor job cleaning out the concrete mixer after they did trial batches. So we ultimately had to send it to an industrial sandblaster to get it cleaned out. Okay, so that's this is has been a very active project for us. Let's head further down into the lab here. Things that we're just looking at along the way here. There's a water jet cutter that can take and cut with nothing but a jet of water. With a little bit of sand mix, it can cut through 6-inch steel plate. We have cool toys here. So now we're going from the small part of the lab out into the big part of the lab. So let's look at how big this building is. This room here is 230 feet long. If we look off to this side here, if we step back just a little bit, We can see we've got a wind turbine blade that's mounted there. We do structural testing of wind turbine blades. We can do blades that are up to 230 feet long. So this is a world-class facility here. So let's look at some of the other things that are happening in this lab. And when I come in, I never know what paths are going to be open. So we'll see what's open today. Okay, looks like we got a clear path here, so we're doing good. So let's keep heading down this direction. So this is the area where the blade would be. It would go all the way down to the end of this room, up to 230 feet long. So now as we take a look off to this side here, you can see these 3 blocks that are yellow on top, kind of a reddish orange on the bottom. Those are actually floating chambers from our floating offshore wind platform. These were built here in the lab. They're made out of concrete. And you might be thinking, Dana, you have lost your mind. Why would you ever make something out in the water that would float and make it out of concrete? In fact, I said this at a meeting in Augusta, and I heard a Mainer in the front row mumble under his breath, well, you make it out of concrete. I know where you're going to find it. It's going to be on the bottom. But we know that you can have heavy things that float, like steel ships, and the key is having enough airspace inside. And we believe concrete is going to be the most durable material, and these are things that we built in this lab. We do big, big stuff in this lab. We're now on the verge of probably next calendar year going to construction at full scale. This is a 1/8 scale floating offshore wind platform. Next year we're going to be going up to full scale, which will be something like a 300-foot tower. So let's keep working our way down in the lab and see what other cool things that we can find today. How's it going today?
Pretty good. How are you?
Learn how to drive the forklift? You're doing awesome.
Thank you.
So we had lots of students that work here in the lab, and the student just getting training, and no one gets to work in the lab until you've had safety training, and then as you learn new activities, you get more and more training. What we're looking at behind me here is the world's largest 3D printed boat. We printed this using the world's largest 3D printer, which we'll look at in just a moment. This particular boat is 25 feet long, weighs 5,000 pounds. It was printed in 70 hours. Let's take a close-up look at what we're seeing here in the side of this boat here. What we have is, you can see that we've got the individual beads. You can see them being laid down at a 45-degree angle, okay? So this started at the stern, worked its way up toward the bow, printing it as it went. The principle of operation of this is a lot like you'd see with a hot melt glue gun. We've got a solid tube of glue, a nozzle that will heat it up, make it pliable, extrudes it, and it sticks tenaciously to the material around it. Same basic operation. The feedstock for this is a mixture of plastic with wood fibers mixed in with it. So this is the world's largest 3D printed boat. So let's take a look at the next really big thing that we have. So this is an example of the feedstock that we have for this is these small pellets here. This is the feedstock, and it comes in a big bin, and it actually gets vacuumed over into the machine. And the machine itself is behind us. So if we take a look out maybe up through here, we've got some clear space. You can see there is the printer. It has the printer head on it. It runs on these long rails. These are 60 feet long. It's 20 feet from side to side and 10 feet tall. So we can do 60 feet long, 20 feet wide by 10 feet tall. This is the world's largest 3D printer, and we have it here at the University of Maine. So let's take a look at what else we have in the lab. We do have some fun things too. Here's a 3D printed map of the state of Maine that came out of our printer. So what we're looking at behind me here is we have a production line where we make medium-sized composite parts. This starts with a blank. So here's an example of a blank where we have individual fibers here. It comes out of a machine that automatically lays this up, and it's got little spot welds that take and hold it together. This, as it exists now, if we take a little bit broader view, that's not very strong. So if we take a look, so we got a machine that lays this up. If we look way up over the top, what we can see is we've got an orange robotic arm. We'll take and pick up this, which is called a blank. It picks it up, puts it into an oven that takes and heats it up, and then it goes into a mold where we have a press that'll take and press it into a part. This particular mold is to make a differential cover on a truck. That's an example of a completed part, so a differential cover off of a truck. We have other parts. This is the original part. This is a rocker arm from a Ford Transit van. Here's the replacement part. The replacement part, you can literally just hold it up between two fingers. Very, very lightweight. So why are engineers trying to take and do this? We're trying to do it because it lowers the weight of vehicles, and that improves fuel economy. That's one of the holy grails of vehicle manufacture, is to make them lighter to improve the fuel economy. So what we have here is you've got a complete production line that takes and will make these parts. And we're studying both how to make it, and if you were paying attention earlier, the how to make things, that sounds a lot like an engineering technology problem. We take and can also, and we're studying the behavior of the material, which is more of an engineering problem. So we're doing that all in this lab here. So let's take and move now into the next part of the lab. So now we're looking at the production line that takes and makes medium-sized composite parts. We have a 3D printer that prints the mold, and this prints with a plastic that has a relatively high melting point, so it can be used in the press and press a hot object against it. So first we're taking and making the mold. The next thing we need to do, if we take a look over here, is we take and make blanks. So we have this machine that's out here that takes and spools off the material. That is the material. It has both the reinforcing fibers in here and the binding agent all in one. So it takes and lays that up. Once it's laid up, we take and go up this way, and we can see the composite, the robotic arm that'll take and pick up the blank, pick it up, bring it to the next stop. So the robotic arm is now carrying the blank to the next spot. And so this is the next stop where we have an oven, so a tray comes out. The robotic arm takes and lowers the blank onto that. The tray goes back into the oven, heats it up to make it pliable. Then the tray will come back out. The robotic arm will pick it up again, then put it in this hydraulic press that'll take and press the part between the two parts of the mold. Then we've got another robotic arm that will take the part out. So this is a completely automated process. What we're trying to do is to prove the technology, because we're going to be able to do this on a large scale in the US. We have to have a very significant, a very automated process. So you can get hands-on experience working on things like this at the University of Maine. So we're now going into the wind wave basin. And as you can see in the background, we got a crew up there working. It's a very active place. What we have right in front of us here is we have a series of 16 paddles that rock forward, rock back, rock forward, rock back. And that's what takes and makes the waves. And if we take and work our way around to the side a little bit, we'll be able to see a little bit more clearly how that will work. So if we take a look down here, what we have is a series of 16 paddles. These rock forward, rock back, that makes the waves. And what we're trying to do in this lab is not to study waves. What we're doing is making the waves we want and study the effect on structures. We've got an example structure sitting right off to the side here, so let's take a look at one of those. So here we have approximately a 1/30th scale floating offshore wind platform. So it's got buoyancy chambers at each corner, plus one more in the center. It has a tower. It has the wind turbine blades. This is a fully functioning unit. This is anchored, so it doesn't float away, but beyond that, this is completely floating. Just for scale, that's a person, okay? So here goes the person back on this. So this is a very, very significant scale structure. And we subject this to waves. And then if we focus in the other direction, so let me walk around here so we can look at the other end of the lab here. So we have up there at the far end, that's the wind generator. So we can generate both waves and wind at the same time. On a scale basis, we can do the equivalent of 100-foot waves and 200-mile-per-hour wind at the same time. So this is a real storm. This bridge that we're looking at right here, this is a tow rail. This can actually now tow the structure through the water. So we can take and do wind, waves, moving all at the same time. Then the final thing we can do is we can take and vary the depth of water. And so when we combine all those capabilities here, this is the most unique test facility of its kind in the world. So I bet many of you students who are watching would like to take and work in a place like this. It's possible to take and get jobs here. As I said, we've got 100 undergraduates who work here during the course of a year. I also know that some of the parents might be interested in working here, and we do have a really cool deal where the child and the parent can share a dorm room, and we'll give you a reduced rate, and you can both come and work here, but the family dynamics, that's on you. So now we're going to take and move on to our next lab. Okay, we're now in the Process Development Center. What we're looking at behind me here is a pilot scale paper machine. What we can do here is literally start with a log and end up with paper. We can make about a 2-foot wide sheet, and we work for companies around the world. There's another example of where students can get hands-on experience with full-scale production operations. So what we have is we've got a machine that can take and grind up and digest the wood, take and lay out the slurry of fibers and water, take and dry it, coat the paper as appropriate, and end up with a roll of material. One of the themes of what we do at the College of Engineering is to have the ability to go from the concept of an idea to actually taking and producing real product. We do the whole thing here at the University of Maine. Now we're in our Engineering and Science Research Building. Here we have Class 1000 clean rooms. What we're doing is making advanced sensors. An example is we made a sensor that can detect red tide. Red tide is something that contaminates shellfish, and if you were to eat shellfish contaminated with red tide, at best you'd get ill, and at worst it could actually be fatal. The normal test to test for red tide is to take some clams that you think are contaminated, grind them up, feed them to 3 mice, come back the next day and see if the mice are alive or dead. If they're dead, you think it's contaminated. If it's not, then the shellfish are good to use. The union that represents the mice really do not like that particular test. So we have a faculty member here who developed a sensor that detects only one thing, and that's saxitoxin, which is what causes red tide. And we do that by taking and having the right base material with very thin layers on top. Some of these layers are only 1 atom thick, and what this makes is a filter that only allows what you're looking for to get down into the detector. So it's very applicable for students in things like electrical engineering, and we have electrical faculty who work in places like this. So now take a look at some of our clean rooms. So behind me are some of our clean rooms. So this is where people would be with their bunny suits because when you're making really small things, human hair is a massive contamination. So we able to take and work in clean space like this. We take a look at some of our other areas here. So if we take a look in space like this, you can see that the color in here is a little bit different. This is where we're doing photolithography, where you can take and make a mask and then use and expose it to the right kind of light to take and actually embed the pattern under underlying material. If we take and move our way further down the hall, okay, so this is where we're taking and actually laying down material that's only 1 atom thick. We do this in an area with a very high vacuum. So we have faculty and students that get to work in world-class facilities such as this. So now we're in Crosby lab. A lot of mechanical engineering projects are currently done in this space here. So you see some of the drill presses and other machining equipment. We do a lot of cool things here. One of the great projects we have is right here. If we take a look at this, this is clearly a snowmobile. But let's look at the back of the snowmobile. That's not a normal snowmobile. This is a snowmobile that we converted to run on compressed natural gas. And this is the cylinder that actually contains the gas. Why we want to do something like that? We're doing that because natural gas burns much cleaner than gasoline. And small engines like we have on snowmobiles, lawnmowers and such, they burn very dirty relative to the engines in our cars. So we were part of a competition called Clean Snowmobile. What we did is we took and changed the fuel to take and produce a snowmobile that burns much cleaner. If we take and look up over our heads here, we can see our USS Maine. This is a human-powered submarine. To be able to operate this, you actually have to be a scuba diver, so it's not a pressurized hull, and we were part of a national competition for that. So one of the things to keep in mind about all of our engineering programs is that we have the opportunity to take and participate in a wide range of out-of-classroom activities. It could be clean snowmobile, it could be human-powered submarine. The civil engineers make and race a concrete canoe every year. They go to steel bridge competition. We have a very active chapter of Engineers Without Borders that have been working in Honduras, very active Society of Women Engineers chapter, and all these are ways that we can take and have our students really participate in the full range of engineering, certainly inside the classroom, but also outside the classroom. We do a lot of work here on unmanned aerial vehicles. This is a quadcopter that mechanical engineering students were working on. And it goes even beyond that. If we take a look at this project here, this is, if we look at the top, this is a sailboat. It's a catamaran, a trimaran actually, but this is one where just under sail power, it will go up on these hydrofoils. And that minimizes the contact of the boat with the water, which allows it to take and go much faster. One of the neat things about one of our faculty members, Dr. Fries, he was part of the America's Cup team for the country of South Africa. So he's a great expert in this. And you might be thinking, is that a mechanical problem? Absolutely, because a lot of aerodynamics in that. And as part of Alex Fries' leadership, that's part of what our students take and design. And for mechanical engineering students, they actually build their projects and it ultimately has to work. So we're on the site of the Ferland Engineering Education Design Center. This is a project we're going to be breaking ground on in May. This is going to be a 100,000 square foot, $79 million building. One of the key features of this building is the Student Project Design Suite. We're going to have 48 workbenches. We can assign a workbench to a group of students for a semester or a year. This is your space, lockable storage underneath, so you can keep your stuff there. You can leave your project parts out on top of the bench. And the benches are surrounded by shops where students fabricate parts. So we're going to have a biomedical engineering shop, an electronics shop, a 3D printing shop, a tool crib, a vehicle shop, a metal shop, a wood shop, and a composite shop. So you go out to the appropriate shops, fabricate parts, bring them together to your bench, assemble them, do your testing and debugging there. This is going to be the best space of its kind in the Northeast. We're going to have on every floor, we're going to have a collaborative classroom where students can learn in a very collaborative manner, working in groups of 6 with a large screen TV at every table. We're going to have our student commons where we've got comfortable seating for students. Food services available, since food is one of the universal lubricants of life. We're going to have individual meeting rooms for between 5 and 12 students. You can take and check those out. So maybe you want to work on homework for a certain problem every night at 8. You can reserve one of those rooms for you and your classmates. This is going to be an awesome building. We're going to have it completed in spring of 2022. So when you come for your junior year, this building is going to be done. So it's been my pleasure to lead you on this tour of the UMaine College of Engineering. We have a lot to offer you. We have great hands-on programs with instructors that you'll know on a first-name basis. We have tremendous demand for our graduates. We had a record 170 companies at our last engineering job fair, 99% placement rate for our students. You're going to do some really cool senior capstone projects, and I hope to see you all at New Student Orientation in June.